Ah, it won't play. It's just.
It's just a recording.
Okay.
Are you ready? All right, very good. So before we start, a quick announcement. So we will take another group photos today, right after the seminar. So there's going to be one for, I guess, where the school is. Or?
Yes, where the school, yeah, right on the side where the school is.
Okay, good. So don't run away right after we take the picture. And I'm happy to introduce today's speaker, Sylvain Fichet, and he will tell us about the warp dark photon.
Oops. Okay, thank you very much. So, good morning. Wait a minute. Okay, it works. Yeah, so it's a recent work I've been doing with Sylvain Fichet and Photon, that some of you know. It's so recent that it's not published. In fact, so recent it's not finished. But basically, it's in this line of work that we have been doing for the previous years of the warped dark sector. So I'm going to tell you a little bit about this idea of a warped dark sector. Then I'm going to introduce, so we are going to study a broken U1 in ADS. So warp space, but mostly ADS. And then from that, we will deduce some class of model with a continuum dark photon. Okay. So this is just, I need to introduce some basics, of course. So the general idea is the following. So we consider, so as usual, in fact, a 5D space-time, which is curved, which has this kind of metric, where z is the fifth coordinate, and in this type of metric, you have a z-dependent factor here, which rescales the whole metric. So when you move along the z direction, you have an overall rescaling, and we refer to this as a warped background. Okay. We assume that this background is truncated at some value of z, so we can think of it as a domain wall or a defect, but I'm going to refer to this as a brain, or UV brain. So typically, but not always, the space-time is considered will be ADS near the brain. But away from the brain, it can be something else. So it could be, it can be ADS, but it can be you can also have a singularity, in which case you talk about a software. You can have an higher brain. You can have an horizon, also. So there are plenty of possibilities, and this really depends on the details of the model. So so that's the background. Now we're interested in fields living in this background, so 5D fields, quantum fields. And what happens typically is that you can have a few modes localized on the brain, or near the brain, while most of the modes are localized away from the brain, so in the bulk. The idea, of course, is to identify these brain-localized modes as the degrees of freedom of the standard model, and then due to the geometry, the typical geometry of the model, what happens is that all the other modes they typically tend to form a light hidden sector. So they tend to be weakly coupled to the standard modes, and they tend to be light. There is you can have a light hidden sector which naturally appears, and so that forms a nice playground for dark sector model building. So here I'm saying dark sector. It's almost the same thing as a light as a hidden sector. Just the name indicates that the coupling to photon is specifically has to be very, very weak or vanishing. So I will be saying dark sector. Okay, so this, of course, this kind of construction is not new. Okay, it has been around for about 20 years now, more than 20 years. So, okay, this can be considered as a continuation of this model building with waterfall dimensions. More precisely, one can think of this as a brain wall model, but with more things in the bulk. So with more matter fields in the bulk, and also and we actually care about these fields that will matter, and also with more things happening in the bulk, like soft wall, horizon, things like that. But today I'm not talking much about this part. Okay, so well, that's theoretically well motivated. However, to make sure that we should spend time on that, we should think about all the possible motivations for that. So I made a list. So first motivation, of course, is that we know there is a dark sector in the real world. So that's an excellent motivation. But okay, that's valid for all kind of dark sectors models. Okay, you don't need to do all these things to model dark matter. Second motivation. So this kind of framework, it gives signatures which are kind of exotic. Okay, they are signatures which should be not really expected if you build extensions of the standard model with just a few extra particles. So in a sense, it's a good example or propaganda for the fact that so actual model building matters for phenomenology. Okay? It actually makes a difference at the level of observable signatures. So for example, in this kind of models, what do we get? We can get fifth forces with non-integer behavior, which you will never get that from simple extensions of the standard model. Along these lines, if you assume that you have this kind of force between dark matter particles, this scattering cross-section will also behave non-trivially, so it will have a non-integer scaling in the velocity. So that's useful for strongly interacting dark matter models. At collider level, so for instance, you can have so what's called sometimes soft bombs or isotropic events with high multiplicity and soft final states. So it's something which is very typical. So it's something which is typical from gauge theories with a large telescoping. So there is a paper from Chaba and John about that. But here this is a computation in their paper there is a computation with KK modes. Here is a computation with directly with a continuum of modes. So it's a bit different. You could also have periodic signals at colliders. So this is here I'm plotting a cross section where some bulk propagator is present in internal line. And so, well, okay, so if your spectral distribution is discrete or sufficiently discrete, you will get a series of bumps like that. So that's quite okay. You could expect that from a simple extension of the standard model, but only if you already had by hand a bunch of modes regularly spaced. So it will look, quite unnatural. And also, by the way, here you have bumps, but you have also dips. And so these dips really they come from the from the collective interference between all the modes. So you will never get that. You never expect that if you were just adding modes one by one to a standard model. Okay, so that's the motivation about signatures. third motivation, so much more specific. So this kind of setup, it provides a model with three continuum, which are automatically, consistently coupled to gravity. So that's interesting for phenomenology. So there are phenomenological studies involving free continuum. So M-particles, for instance, it's basically a free continuum, and that's completely fine. But when you involve gravity, if you have a free continuum, you will meet problems. So basically, the claim is that a free continuum cannot couple to 4D Einstein gravity. So this is something which is actually well known from the formal CFT side, but just with a different language. Okay, they will say so the free continuum, they will call that a generalized free theory or generalized free field, and they will say a generalized free field does not have a stress tensor. So if it doesn't have a stress tensor, it cannot couple to gravity. It's just one way of formulating the thing. For fifth force?
Yeah, like the previous slide, 1/r.
So
the non-integer is always what is the number.
So I can be aware.
Non-integer number in the power of 1/r is what typically.
It really depends. You know, it's more or less a free parameter, but okay, a force, your force in 4 dimensions, it cannot be smoother. It can go slower than 1/r. So all the force they will have a steeper potential behavior than 1/r. Yeah. So back to continuum. So from the CFT side, it's very clear, but it's also not very difficult to generalize this claim to a continuum which is not conformal. We discussed that in a recent paper with Eugenio, who was here, and Mariano. And so now it's interesting to think about what can we do to avoid this fact. So basically, we have to cross one of the terms in the statement. So for instance, if your continuum is actually secretly a discretum, so a set of discrete modes instead of an actual continuum, then your problems are solved. Your continuum could be almost free, but not free, in a way that makes the theory consistent. So it's typically what happens for large n-gauge theories with n large but finite. So there are interactions. They are n-suppressed, 1/n suppressed. But there are interactions. Your continuum will be almost free, but not free. Finally, you could cross here Einstein gravity. So instead, if you have some kind of modified gravity, you avoid the claim again. And so this is what happens in holographic theories, as the one we are discussing here. Basically, automatically, the graviton gets the law of gravity gets modified. Graviton itself gets a continuum component, so it's not Einstein gravity anymore. Okay, and there are also effects happening for cosmology, but I will not talk about that today. This whole thing is just to motivate a bit the overall scenario. Finally, so before moving on, I will just mention quickly that when we play with this kind of theories, even if you focus only on phenomenology, very quickly you have difficult theoretical questions which happen. And so in these examples, these examples are focused on loops in ideas. So of course you are doing QFT in ideas. At some point you wonder about loops. it turns out there are plenty of things to do. It's very technical, but there are interesting things. Well, there are interesting things to do. And so, for example, in these papers, we have shown, so after a period of confusion, we have shown that so there's a notion of opacity in the bulk for propagators with space-like momentum, which is trivial, but also for propagators with time-like momentum. And this is induced by the dressing of the bulk propagators by bulk interactions. Also, I've made some calculation of dressed, so propagators in IDS dressed by bulk interactions, and also recently I computed explicitly some brain localized operators which are generated at one loop. So everyone knows that, but it was not really computed in the literature. So I made some explicit computations along these lines. Okay.
What does dressed propagator exactly mean? You include some bulk loops? Or?
Yeah, something like that. So bulk loops, simple bulk loops, just a 5-free interaction, for example. And you already have plenty of things to do with that. Some computations are exact, others are approximate. Yeah. But okay, so I'm not talking about that today. It was just way to mention that in case someone is interested to discuss further. So now let's finally go to the model. So broken U1 in Mars space. So it's very simple. We put a U1 gauge field in the bulk and a charge scalar, and we assume that there is a potential on the UV brane which gives a non-zero wave to the scalar, and so it spontaneously breaks the gauge symmetry. So before getting into troubles, I have to mention that there's a bunch of works about that. So about related to this. So for instance, about unbroken gauge fields, there are these papers. Gauge fields broken by boundary conditions, these papers. It's usually in presence of two branes, I think. Also in this paper, there are studies more in the context of RS1. I hope I did not forget a major contribution. Okay. And so what we are doing will be substantially different from what is shown here. Okay, so we have this simple looking system, and we can wonder plenty of things about it. So what about the back reaction of the metric induced by the wave? What about the spectrum of the UN field? What about the Gauss-Storm equivalence theory? So in fact, this one, I will not talk about it, but if someone is interested, we can talk afterwards. What about the holographic dual of this kind of setup? And also, then you can ask more phenomenological questions. So that's basically more or less the outline of the rest of the talk. So I'm showing the action really quickly, just to, you don't have to remember anything, just to show more or less what we are doing. Okay, we work in arbitrary dimensions. We included brain terms for the photon, for the gauge field and for the Higgs. Okay, that's it. No need to spend time on that. Now the important thing is that is the wave. So the wave is so in fact there are two solutions, but we select one solution, the solution which is localized near the UV brane. this is, so sometimes this is exact, sometimes this is some kind of simplification or approximation. And so this there, okay, it depends on just on two parameters. This is the value of the wave on the brain, and this is a parameter which controls the profile and which comes from the bulk mass of the scalar field that I will call the Higgs. Okay, so first let's think about the back reaction. Looking at the 5D Einstein equation, you can see that the back reaction so a large back reaction will show up when the contribution of the wave becomes sizable compared to the cosmical constant. And so, okay, just making some comparison, one can see that a large back reaction will occur when alpha is smaller than d/2. And one can also estimate the position at which the back reaction appears. Okay. Okay, one can check that there is always a region near the UV brain where space remains ADS. Okay? So we check that these things make sense parametrically. So we could, in principle, compute the whole system. Okay, we know the technology for that. Here, for this work, we did something simpler. We simply assume that there is an higher brain whenever the large back reaction becomes large. So okay, we just cut off the higher part of the bulk as a simplification. Okay, so when there is back reaction, we put an higher brain at this position. Okay. So next step. So now we know the background. So now what about the spectrum of the gauge field over the background? So this is the equation of motion, and the contribution of the wave is here, where I introduce this parameter NA, which is V0 times the gauge coupling. So it's a not so easy differential equation. It doesn't have general analytical solutions. So what can you do? So it's possible to find solutions sometimes for specific values of parameters, but we don't want to do this. We really want a complete understanding of what's going on. What can you do? First, okay. So for the rest of the talk, the important parameters, these are these ones. Okay? So the alpha I already showed before, which controls the profile of the wave, and this MA here, which is in a sense the mass of the gauge boson on the brain. So everything will depend on this, principally on these two parameters. Okay. So what can we do to solve or to understand this thing? We do we use the WKB approximation. That's a well-known trick which has been used already for extra dimensions. So to do this, you have to do some filter definition to end up with a Schrödinger-like problem, and you get a Schrödinger potential like that. And the solutions. The WKB solutions look like that. And so a first thing one can see is that so when alpha is smaller than d/2 minus 1, this here can be 0, which means there is a turning point, which means there can be discrete modes. And the WKB approach also tells us what is the mode spacing between these nodes. What is the spacing between these nodes? Okay, there is it's given by this formula here. Okay, so that's nice.
So what do you mean by turning point?
Sorry?
What do you mean by turning point of the potential?
Yeah, so it's so turning point is when Vz prime equals p squared. Yeah. And so in the WKB language, it's okay. So WKB approximation breaks when you are in this region. But you can do matching between the two, so on each side of the turning point, and you can okay.
No, it's the I just want to know what the turning point
Yes.
is. I understand.
Yeah. You use that in a paper of yours, by the way. Yeah.
How many years ago?
10 years ago.
Okay.
No, it's true. And so, okay. So first conclusion, it turns out that for alpha smaller than 0.2 minus 1, we have discrete term with this spacing here. So not a trivial exponent. For alpha equals 0.2 minus 1, we have a gaps continuum, and for alpha equals 0.2 minus 1, larger, we have an actual continuum. And so this is quite solid because okay, we checked that. So for alpha equals 0 and equals 4, for instance, there is an identical solution, and we can check that this matches the WKB calculation. And also for this case, there is also a simple analytical solution giving rise very explicitly to a gap continuum. This is a result very similar to a paper from Giacomo and John, where basically they did kind of the same thing for scalars and fermions. So here, in a sense, it's the same idea which appears, but for a gauge field.
So when you say discrete, do you mean a few discrete nodes followed by the continuum, or just discrete nodes all the way?
So here it's a full set of discrete nodes, so an infinite set of discrete nodes. Here you could have, so below this value, you could have, I think, one discrete node. Yes, only one, I think.
So here you don't have an IR brightness.
So I'm coming to this right now, because, okay, this looks nice and simple. However, I just said 2 slides ago that if there is a backcorrection, we put an IR brain, which will change everything.
But
So
you wouldn't get a continuum if you have an IR brain.
right. But so how does this make sense? So what happens is that when you have an IR brain, so here this is IR brain at ZB, okay, that I introduced earlier. The Schrödinger potential can be understood as a potential like this. There are various ways to understand this. A way to see it is really just using the formula for the mode spacing, which depends on. Right, okay. I don't need to go too much into details now. So the point here is that for nodes in this region of the potential, the presence of a higher brain does not matter. Approximately at least. So really there are two regimes in the spectrum, and the nodes in the bottom part of the spectrum are independent of what happens further here. You can find also this kind of intuition for potentials of like atomic systems, for instance. But usually the potential starts steep and gets softer. While here we really have a wall when we go at high values. Okay, and okay, so you can parameterize this in terms of number of nodes. Okay, so there is the transition occurs at some value n star, and using some parametric estimates and putting the correct dimensional analysis values, one can check that there is no problem. This n star can be very large, so you can have plenty of nodes in this region of the spectrum.
But at some point there will be a singularity in the length, because I mean, in the region where the back reaction is very big, do you expect? You can probably even solve the coupled scalar gravity system, yes?
Yeah. So this is in the to-do list that for the next paper. But what I'm doing here, it's a simplified approach. So I'm removing the large back correction by putting this brain. So this is by construction. This is automatically mostly ADS.
And it's coming in before there's a large back reaction.
Yeah. It's precisely it's on purpose made for that. So to cut off the region with a large back correction.
So gravity is not going to have a gap continuum or anything?
Sorry, gravity?
Will not have a gap continuum or anything like that, at least in your approximation.
Absolutely. So you have this thing affects only the U1 gauge field, but the background, the background itself, the space and background remains ADS. So gravity and also other fields which could be around, they will not be affected by this. So they will not get gapped. Well, okay. Okay, well, there is a higher brain, so okay, maybe, okay, depends on details. Okay, so moving on, what else? Yeah, so now let's think a little bit about the holographic CFT. So I focus on alpha larger than 0.2 because there is no back correction, it's safe. So the wave is very localized towards the UV brain. Very sufficiently localized towards the UV brain, so that there is no back correction in the bulk. It remains ADS everywhere, so you can safely use the ADS CFT. We focus on the so-called holographic self-energy, which is basically a piece of the brain-to-brain propagator, and which is a piece from which we can deduce the behavior or the content of the holographic of the dual CFT. If it exists. And so here we can see two cases. So for when alpha very large, so the wave is very localized towards the brain, very steep, we find that so this behavior here, which means that the CFT contains a U1 current with this dimension. And this dimension automatically implies that the current is conserved. For alpha equals 0.2, instead we find a formula like that. So this scaling here receives the correction. And so this means that the CFT has a U1 current with dimension d-1 plus this correction. So it's gamma G, which is proportional to V0 squared, or MA squared. And this automatically means that the current is not conserved. So we have a CFT current which is not conserved. So that looks interesting. And now we could wonder if we are able to reproduce this from the side of really a CFT construction. Okay, starting directly from a CFT side. So d-dimensional CFT side. So I will skip this part because most of the things work, but the most interesting part was to try to show that how this correction appears from the CFT, really from the CFT side. So correction to the dimension, which will be proportional to the V0 square. So I have some idea about that, but I didn't have time to really finish understand and finish the calculation. So I'm pretty sure it's doable, and I'll be happy to discuss with people about that. But right now, I will just skip this part and go. So there are three slides that I skip, and we go directly to the summary. So this is basically the landscape for the broken U1 in ADS. So as a function of alpha, we have so kind of a discretum, a gap continuum, a continuum. We can have backcorrection or no backcorrection. When there's no backcorrection, we can think of a holographic dual. Here, I'm not trying. And before moving on, okay, I will just mention that we also studied. So this, so we studied the model for alpha equals 0 plus epsilon. So okay, so near this region here, okay, so unsurprisingly, we find that we can think about some kind of CFT dual, but with an anomalous dimension, which will run slowly with the energy proportionally to epsilon, basically because the conformal symmetry is very softly broken for small epsilon. And so the breaking of conformal symmetry will show up only on large, over many scales. Okay, so I'm just mentioning this for completeness. Okay, so now I have 20 minutes. So okay, we have understood parts of the model. So now let's try to build dark photon model. So we do something very simple. We assume that we have photons on the brain, like visible photons, and we put a kinetic mixing on the brain directly, so with a parameter epsilon. And so the photon propagators get dressed by insertions of this bulk U1 field, and that's how the visible sector knows about the dark photon. Okay, so this is basically the usual dark photon construction. Just more complicated, but the structure is the same. In fact, you can also check that you can diagonalize so you can diagonalize the system as done for 4D dark photon models using a field redefinition, which involves the brain value of the dark photon field, and everything. We check that everything works out. Okay, so that's a pretty simple model. So now, okay, so I will in the following I will focus on these two cases, a gap continuum and this particular case, which has a CFT dual. So alpha equals 1, alpha equals 2. So very quickly, so the dark photon, so in these cases get so as non-trivial spectral densities, and spectral densities they contain a continuum, but they also contain an isolated resonance. And for what we want to do, we want to get rid of it because it's too much 4D-like. So we really want to focus on really continuum-like physics. And so, well, okay, one just has to play the parameters to make sure that this resonance is heavy enough not to influence the physical observables, basically. So, okay, that's just an example where, for alpha equals 2, where this is the resonance, but if you increase MA, the resonance gets more and more into a continuum. At some point, it's just hidden in the continuum, and the physics happens because of this region. Yeah. Okay, so if just simplifying as much as possible, taking away all the parameters and all that, we get this kind of spectral distributions. So that's for the gaps case. Okay. So it's a distribution which starts at NMA, and then it does something like okay, something like that. And the okay, so for alpha equals 2, we have in this limit we have essentially a conformal a CFT-like dark photon. So the dark photon propagator is essentially like a 2-point CFT correlator. Okay. So now something maybe more interesting for some people here. Okay, so I could do phenomenology, so go through all the bounds one by one and so on. So instead, here we try to use the existing bounds, which are released everywhere, on normal dark photons, so on 4D dark photons. You know, this kind of landscape of bounds. Okay. So it's interesting. So we can try to extract, deduce bounds on our model from this kind of plots. So can we do this? The answer is yes, and yeah. And so it's I think it's a interesting enough problem to be formulated in a more general way. So, given a bound on standard particle with spectral distribution like that, so normal particle, can we obtain a bound on a model with an arbitrary spectral distribution? So this is really what we are trying to do. So the answer is yes. So basically, so there are some conditions. So one way of doing it is the following. So if your observable for the standard particle looks like that, and your observable for the continuum model looks like that, with one spectral integral, and if also the observable is independent on hidden assumptions on the mass, then you obtain an exact formula which depends on the profile. So which depends here on the profile of the exclusion regions. And this formula so tells you that the bound on the epsilon of your continuum model here is given by the convolution, by this convolution. So the inverse of the epsilon 4G squared convoluted with the spectral distribution. So I kind of like that because it's fairly general, and also can be applied to any continuum model you have, and even if you have, for example, a tower of particles, it also works. Okay, in this case, your row becomes discrete, and you get a sum here. But in principle, the approach still works. So that's kind of nice, I would say. All right, so okay, so this is just a reminder of how the usual bounds on dark photons look like. So if you apply the the approach I told you earlier, you get this kind of result. So compared to this, we can say that the landscape of bounds is quite modified. It's quite deformed. Typically, what happens is that the bounds from low masses get they lose compared to the bounds from high masses. So here the big winner is the stellar constraints, which completely overwhelm the bounds from field force and CMB. We have also computed some projections for Bell 2 and NA64. And okay, we find that they can probe a part of the parameter space.
Sorry, I may have missed it. So how exactly are you adding the kinetic mixing? Where is the standard model? Is it in the bulk?
It's on the brain. It's a brain localized operator.
So on the IR brain, the standard model is on the IR brain?
No. There is no. The IR brain serves just. I mean, everything is on the UV brain. It's like
standard model is on the UV brain.
Yeah.
The extra stuff is the bulk, and then you add the brain localized.
Yeah. So it's like a brain wall. So everything is near the UV brain. And the IR brain is there just to get rid of back correction if there is. Right.
But the standard model doesn't go in there.
So as I mean, it could, but then it becomes a more involved model. So here I'm really focusing on the much simpler thing possible. So yeah, that's it.
So, sorry, Sylvain, can you remind me why the stellar bounds in the usual case close for small masses and why here they actually become independent mass?
So,
stellar constraints here they tend to close for very small masses, right? They're not effective.
yeah.
While in your bound, they just become independent of the mass.
Right.
Why is that?
Well, it's due to the convolution. So we have a distribution in mass which is continuous, and we convolute it with this shape here, basically following the formula I showed before. And so, well, depending on this continuum distribution you have, you will tend to pick always, the strongest peak here. And that's basically the reason why these shapes become different. Okay, and so for alpha equals to 2, everything changed again. Now the star cooling bounds go in this direction. They kill they dominate over this NX64 bound, for instance. While there's still sensitivity for Bell 2. Okay, these are just examples of bounds. Okay? I'm not going into all the details of which parameters does what and blah blah blah. It's just to give an overall feeling. So finally, last result. Well, last example. So one can think of a simple dark matter annihilation cross-section mediated not mediated by dark photon, but into dark photons. These are T channels. So this is a classic classic process in presence of dark photons. And we can look at what happens. And so what happens is that so this will be here the standard result. So this line here, and when you put a continuum dark photon, the result gets substantially changed. So the shape of the curve changes, the magnitude changes. The details depend now on the other parameters of the model, so they depend on the kinetic term of the photon, the kinetic term of the Higgs. Okay, there's parameter dependence like that. But okay, I don't have to talk about that, to annoy you with that. All right, and so that's it. So I just summarize. We have studied a model of so a broken neuron in a truncated ADS. Using that, we introduce a model or a class of models with continuum dark photons. We have computed some bounds for some benchmark cases. So I presented here a case with a gapped continuum and with with course a conformal dark photon. And there are plenty of things to do. So, for instance, solving the full system. In this case, we have the scalar gravity system and see what happens to the photon. Understand more the CFT dual. Understand more the equivalence theorem. It's interesting to. It will be interesting. In fact, we already started, but it will be interesting to do. To study cosmology in the full models when there is a back reaction in the bulk, because important things happen because of that. And of course, it will be interesting to explore more all the experimental signatures. For instance, with other cases, with other spectral distributions, looking into more details at collider signatures and so on. And so that's it. Thank you very much.
Questions?
So in this instance, then we go with the dark matter. The dark matter interaction is again in the UV plane.
Yes. So yes, so dark matter again, very simple. Dark matter is on the UV brain. And it exchanges a bulk propagator. Yeah. Oh, okay. It's not this process, but okay, you see what I mean.
So I have a sort of intuitive confusion. So what you said is that you sort of have a potential valve, and then on the bottom of it you get, this gap continuum. While in the background that Gero and Mariano suggested that we looked at recently, it was very different. That there was a falling potential that was going to a constant, yes. And in that potential, I understand why there's a gap continuum, yes, because there's a potential that is falling, goes to a constant, and there are just. But in a valve, I always thought that quantum mechanics is telling you that you're supposed to mainly have discrete bound states, and only once you get sort of above the energy of the valve are you going to have a continuum. So I'm just confused how a potential valve, and you are sort of saying that you are on the bottom of it. Yes, the thing that made me confused is that you said that, well, it's completely insensitive to where you put the IR plane. Yes? So for example, in this other background, the modes that are very close to the gap, yes, they are actually the ones that see the singularity, that go all the way to the.
Right. So I think the answer to that is that. So for this limiting case, okay, it's a possible answer, but I'm not completely sure. So for this limiting case, the IR brain is very far away in the bulk. But
so we should have discrete now. So whenever you have a well that's discrete, there's no way out.
Sorry?
That's what I saw also.
Yeah,
the way you get the gap continuum is that you don't have a value, you just have a falling potential, but it doesn't fall to zero, but it falls to
a constant.
and then that's the gap, and you just have the continuum state above that. But then of course, that constant, the modes that are close to the constant are the ones that go way in, yes? So they are very sensitive to the singularity.
Right. I think I agree with that, in fact. So maybe the picture I showed was too rough or too.
I would like to understand, I mean, I'm sure you solved the equations correctly, yes? So I just want to see how do you really get the complete, what's the way around it, yes?
Yeah, so I don't. Okay.
We can talk about it.
Yeah, I don't have a clean answer right now. I need to think more. Yeah, using what I said in the talk, there should be an higher brain, so maybe very far, but there should be one. So maybe in this case, the gap continuum has a very tiny. So it's discrete with tiny steps.
Yeah, that makes sense. Although if you go to the diagram very far away, then above the gap, continuum, but still it's discrete. Is that,
Yeah,
is that what you call the discrete one?
Yeah. So it's you have like a tiny discrete. I guess so. Yeah. I mean, if following what I said, it should be that.
But then you get into the back direction.
The back question doesn't matter because the higher brain is there to whenever, by assumption, whenever the back correction shows up. Just by assumption.
Right, no, I understand that, but I mean, if you say, okay, if you want to, you have to see that the scales, I'm sure you did it right also, no, the scales dimensional, so you can, if you want to have the spacing that is very small, for instance, compared to the gap, so you have to make sure that the back correction only appears at sufficiently large Z,
Yeah, sure. But this we know. I mean, this part of the estimate. But I agree. There is something to think about more. I guess. Yeah.
Can you the dark photon parameters page?
So like these plots.
Yeah. So when you go to the dark photon mass here is still the 5G gauge coupling times the value of the Higgs.
Yeah. So this MA here, it's
there you go.
it's that.
So if you go to large masses, do you have to worry about the back reaction of the Higgs if just the value of the Higgs pad becomes too large towards the IR? Or do you think so?
Yeah, well, it's typical. If you go, so wait. What are the assumptions?
I'm just saying that if you go to large masses, then I expect that V naught might become big, right? And that's the value of the Higgs.
I don't think I see the. No, sorry. I don't think.
Yeah,
I
the
see.
same.
The scale of the plant brain is probably unplugged, yes?
Yeah, that's true.
So this
So
is
probably
still
outside of the plot.
pretty small on the yes.
Yeah.
But then, at some point, it is growing in the IR, so like you said, at some point, it will become large. The question is, can you make it as big as you said on the plot and still have the IR frame so there's not affect
So we can discuss later. Maybe I didn't understand exactly what you had in mind.
Yeah, I have a very simple question. What happens if you compute k to pi dark photon in this plot? Because usually these constraints are not very important for the standard dark photon. Because of conservation of the electromagnetic current. But here, some of the constraints that vanish for the same reason seem to stay flat at the low mass. So maybe that type of constraint.
Which process again?
So k to pi.
Hey.
K pi.
K to pi. I don't know. So it's you have one or two dark photons in the
So
final
it's
state.
just the emission of one dark photon
Yeah.
in a flavor changing neutral current.
Right. Okay. So this.
Because usually that's suppressed by like powers of q squared over dark photon mass or things or a dark photon suppressed it. In any case, it has a similar shut-off behavior to the solar constraints.
Yeah, so I don't remember seeing this bounds on this kind of summary plot. I mean, okay, it's there. I remove here a part because it was for stable photons. If we didn't include it here, probably it was subleading. But I can check. Yeah. Right now, I don't remember.
Why does this not play a role for low masses in the regular case?
Sorry?
Why you said something why it's not important in the regular case? I mean, if you go back to the one slide back.
Because usually they shut off as a power of the dark photon mass, and as you get lighter and lighter,
So you get a shape
the
like that?
same thing happens for these meson decays.
So you say to the light mass, it shuts off to the light.
Exactly.
Why is this?
So it's related to the conservation electromagnetic current. Essentially, this makes the dark photon case special. If you take other types of light vector models that don't couple into electromagnetic current, you're going to get very strong constraints from meson decay.
I would say, so if it has this shape, I will expect it's hidden here behind this Baba region. I would say that.
The question is, when you lift this suppression, they may be stronger than the collider constraints. But I'm not sure if you lift the suppression or not. Naively, from the stellar constraints, it looks like you do, but I'm not sure.
Yeah, okay.
Any more questions? You're listening, Sylvain, again? So let's go for the photo and then lunch, yes? And what time is the colloquium today? 2 p.m. there is a colloquium by John today. Do you remember which room? There's the lecture at the school.
Yes.
Right. It's very interesting. I would like to understand your way of getting the dark photon. We are thinking a little bit about dark photon in his background. So.
Okay. Which background?
I mean, what do we call it?
The
The soft ball, the one that is a singularity.
The one which gives the gap continuum?
Yeah, the one that gives the gap continuum.
Okay, the special one.
Right, the special one.
I can call it the marginal one or something.
Yes. Okay, let's go for the photo.
Too big.
No?